So today we're just going to talk about how to calculate flows and velocities in open channels. So on Monday's class, we just gave a bit of an introduction to some of the terms we use in open channels, and we talked about the channel geometry, but we didn't really talk about the fluid properties of the channel, which are flow and velocity. So in order to understand a little bit about how these equations work, I want to start by first analyzing an open channel based on the information that we already know, based on the methodology that we already know how to use. So let's say that we have an open channel. We're looking at it in profile view, which means that the channel flows in this direction. This is the surface of the channel. This is the bottom of the channel. The channel has a slope of theta, an angle of theta, and the depth throughout the channel is constant. It's just a depth of y. Okay, so that's pretty much what we have. A pretty simple channel. If we were to apply the energy equation to this channel, and we apply the energy equation just like we've done in the past for pipes, but if we were to apply the energy equation to this channel, we can set the inlet and the outlet, right? So my question would be, if you apply the energy equation, you're already familiar with the energy equation. You know, the energy equation says that the pressure terms, the velocity term, and the potential term, which in this case, we're just using the coordinate system, we're just using y, so I'll just call it y1, equal the pressure term on the outlet, the velocity term, and the elevation term, and any head losses. We don't have pumps, we don't have turbines, so we don't have to include any of these. So if we look at these two systems, typically when we're dealing with control volumes using the energy equation, we look at these energy terms at the centroid of the control surface. However, in this case, because both of these control surface, inlet and outlet, they have the same depth, and you know that the pressure term is just gamma h. If they have the same depth, then can we say that their pressures are going to be the same or not?
At the same depth, they should be the same.
Exactly, right. So if they're the same pressure, because they have the same depth, we can cancel out the pressure terms. Likewise, if our system is steady and uniform, which means that there's a uniform flow rate, and the cross-sectional areas are the same, we know that the velocities are also the same, and we can cancel them out. So what we're left with is an equation that gives us the head losses as a function of the drop in elevation. In other words, if we were to solve this equation, we get y1 minus y2. y1 is just the elevation at this point, y2 the elevation at this point, is equal to the head losses in the system. Now we can call this difference in elevation just delta y. And the head losses can be calculated using Darcy-Weisbach's equation, which is friction factor times length over diameter times the velocity head. Now, when we're dealing with systems that are not circular, that are not pipes, in place of the diameter, we're going to have to use a characteristic length. And that characteristic length is 4 times the hydraulic radius. And from Monday's class, you may have recalled that the hydraulic radius R is simply equal to the ratio of the cross-sectional area to the wetted perimeter. So in the place of the diameter, we're going to use 4 times the hydraulic radius. So we get this form of the equation, right, that essentially gives us the energy balance in this channel. Now, if we look at this delta y, we can express this change in elevation by looking at the angle and looking at the length of the channel. And what I'm going to do is I'm just going to draw a triangle that represents this length of the bottom. So if I draw my triangle here, I know that this is just the length of the channel. And if this is the length of the channel, then I know that this drop, so the distance from here to here, is simply the drop in elevation. You can see that we have an elevation here of y1, an elevation down here of y2. Therefore, this is just y1 minus y2, which we also call delta y. If we set the horizontal direction to be our x direction, we can also call this delta x if we want to. And we know that the angle for this triangle is theta. So based on this information, we know that delta y is simply L, the length of the channel, times sine of theta. So I'm going to write it down, L times sine of theta. And we get that L times sine of theta equals friction factor times length over hydraulic radius times velocity squared over 2 times 4 is 8, so 8 times gravitational acceleration. Now, why am I doing this? Notice that we have length, we have length. We can just cancel them out and express this equation in terms of only the angle, the slope of this channel. Now, in nature, right, most open channel flows found in nature are going to have slopes that are actually very small. In fact, you'll see that unless we're dealing with systems that are in mountainous areas, right, such as islands or some of the larger mountain chains here in the United States, most rivers are actually going to have very, very flat slopes. I would say you will see slopes to go no higher than 10 degrees. Okay? So if most channels are going to have very, very small slopes, no greater than 10 degrees, then we can apply some trigonometric approximations to this angle. So we know that for very, very, very small angles, so for very small angles, we get that the sine of an angle tends to be equal to the angle. Or we also get that the sine of the angle tends to be equal to the tangent of the angle. Now, why is this? Because we know from geometry that for very small angles, as the angle tends to 0, the sine of that angle also tends to 0, and the tangent of that angle also tends to 0. So what I can get from this geometric approximation is that the sine of the angle for very small angles tends to the tangent of that angle. So what I can do is I can express this equation to be approximately equal to the tangent of the angle of this channel. And we know this will be equal to the friction factor times the velocity squared divided by 8 times gravity times hydraulic radius. Now, if you look at this, system, right, you can see that the tangent of the angle, tangent is opposite over adjacent, then the tangent of the angle is equal to delta y over delta x. So I can say the tangent of the angle is equal to delta y over delta x. And this is a term that we use in water resources engineering. We just call it the longitudinal slope, okay? So this S simply stands for longitudinal slope. And it is equal to the ratio of the drop in elevation over the horizontal distance traveled by that channel. So the drop in elevation from here to here over the horizontal distance traveled by that channel. So I can then write my equation as simply saying that the slope equals the friction factor times velocity squared over 8 times gravity times the hydraulic radius. And this allows me to solve for the velocity in an open channel. The velocity of an open channel will be equal to the square root of 8 times gravitational acceleration times hydraulic radius times longitudinal slope divided by the friction factor. So this is the velocity equation using the Darcy-Weisbach equation. You may hear that some people call this the Darcy-Weisbach equation for open channels or applied to open channel. So there you have one way of expressing the velocity of the open channel. And if you notice, with the exception of this new term slope that we've introduced, this equation is pretty much what we've been using when we use the energy equation. It's simply a way that allows us, right, to calculate the velocity of the channel. However, we have a couple of issues here because notice that this depends on the friction factor of this channel. And this friction factor depends on not only Reynolds number, right, flow regime, but also the material of this channel. And Reynolds number itself is a function of velocity. So we're going to have to do a little bit of iteration to use it correctly. Let's recall that most open channel flows are very turbulent, and because of that, the Reynolds number may not affect that much because it's going to be so high that a variation in Reynolds number will not really cause a significant variation in friction factor. But for the purposes of this class, right, since this is an entry-level class, we must look at friction factor and see what actually we need to calculate. And we know that to calculate friction factor, we need the Reynolds number. And to calculate the Reynolds number, we need velocity, which means that to get this, we need this, and to get this, we need this. So we end up with a bit of an iterative loop here. So there's got to be other ways to solve this equation, right, to solve for the velocity of a channel. I mentioned that because most open channel flows are turbulent and very, very hard to model analytically, we've actually relied on empirical values in order to solve for the velocity in open channels. So we're going to start today by talking about the Chezy equation, which is an equation that is derived from a series of measurements. So Antoine de Chezy, a French hydraulic engineer, found that the velocity of flow in a channel was somewhat proportional, right? Was proportional to the square root of the hydraulic radius times the longitudinal slope of that channel. And at first sight, this may not seem too similar to the Darcy-Weisbach equation, but we'll see that it actually is. So Chezy set his factor of proportionality. He just called it C. So we can say that the velocity in an open channel is equal to a coefficient that we call the Chezy coefficient times the square root of the hydraulic radius times the slope. And now if you look at the Chezy equation and you look at the Darcy-Weisbach equation, you can see how they are similar. Because if you look at the Darcy-Weisbach equation, you'll see that we can express the Darcy-Weisbach equation in a way similar to the Chezy equation by separating this term from the other terms. In other words, if I take the Darcy-Weisbach equation and I separate the square root of radius times slope from everything else, I get that the Darcy-Weisbach equation gives me the square root of 8 times gravitational acceleration over friction factor, that's just one term, times the square root of the hydraulic radius times the longitudinal slope. And here you can see that we find an expression, right, for a term that's equivalent to the Chezy coefficient. Now, I say equivalent, I don't say they are the same because this coefficient actually comes from measurements, right? From empirical measurements. And this comes from an analytical study of the channel. So they are equivalent in that if our empirical measurements and our analytical study are both correct, they should be the same. However, because there's always variations in our empirical measurements that we cannot account for, we can't expect them always to be the same. However, this gives us a way to relate the Chezy coefficient to the friction factor. Because you see here that if the friction factor increases, the Chezy coefficient should actually decrease. So there is somewhat of an inverse relationship here, okay? So that's how we relate the Chezy coefficient to the friction factor. Remember, the friction factor itself depends on Reynolds number, so it's not very helpful. However, there are tables that give us the Chezy coefficient, and you'll see that the Chezy coefficient will depend on the channel's geometry as well as the channel's roughness. Now, the Chezy equation is actually very rarely used nowadays. Typically, we water resources engineers use it when we want to have a very, very rough estimate of flow rates. But if we're calculating some very specific, very exact values, we wouldn't really turn to the Chezy equation. Because several years after Chezy derived this equation, an Irish engineer named Robert Manning came up with another equation that we call Mannings Equation that calculates velocity and takes into account the channel's geometry in addition to the roughness in order to calculate this coefficient. So Robert Manning was an Irish engineer who compared different empirical measurements from different sources and found relationships that allowed him to come up with an expression, an equation for flow rate in an open channel. The equation that Manning came up with is called Manning's equation or the Manning equation. Although because he relied a lot on Chezy's analysis. Sometimes we call it the Chezy-Manning equation. Now, what Manning found was that the velocity in an open channel was actually related, right, to the following terms. It was related to the hydraulic radius to the power 2/3, the square root of the longitudinal slope, and then the roughness of the channel. So the roughness of the channel was quantified by a coefficient that was originally called the Cutter roughness coefficient, but that today everybody just calls it the Manning's roughness coefficient. I think even your book will call it Manning's roughness coefficient.
The coefficient for R, we can't quite see it.
Oh, 2/3, 2/3. Let me just write it a little bit bigger here.
Thank you, sir.
No problem. So this was Manning's equation, right? Manning related the velocity of the flow to the hydraulic radius to the power of 2/3, the longitudinal slope to the power 1/2, and a roughness coefficient that we call Manning's roughness or Cutter's roughness coefficient. If you look at Manning's equation, you can see how it can be related to the Chezy equation, because you can just separate this hydraulic radius in two terms that when multiplied give r to the power 2/3, and then you'll have your relationship between the Chezy coefficient and the Manning's coefficient. So if you want to write Manning's equation to take the form of the Chezy equation, then you would get that the Chezy coefficient would be equal to the hydraulic radius to the power of 1/6 divided by the roughness factor, and all this multiplied by the square root of the hydraulic radius times the longitudinal slope. You multiply these values, you end up at Manning's equation. So this term, hydraulic radius to the 1/6 over n, should be equivalent to the Chezy coefficient. Again, I say equivalent, not the same, because these are empirical measurements. Therefore, they won't be exactly the same, okay? So equivalent doesn't mean that they have to be the same. It just means that if our measurements are all 100% correct, then and only then they will be the same. Now, Manning's equation is the most common form of an equation for velocity in an open channel that is used today, particularly because it's very easy to use, it's very easy to calculate. Notice that all we need is the geometric properties of the channel and then the roughness of the channel. However, Manning had a problem. He was an Irish engineer, so he used English units for his measurements. But Cutter was not Irish. Cutter was somewhere in Greater Europe. And therefore, Cutter used metric units to find all of his values for n. So when Manning wanted to publish his equation, if he wanted to publish in Ireland, he needed to use English units, but all of these values of n were actually in metric units. Now, here's the problem. When Cutter measured these values, these were supposed to be empirical values, empirical dimensionless coefficients that gave us friction. So just like the friction factor is dimensionless, the n had to be dimensionless. But if you do a small dimensional analysis of Manning's equation, you'll see that n cannot be dimensionless. So we do a dimensional analysis. In order for Manning's equation to be dimensionally homogeneous, n has to have units. So let's do that quickly. We get that Manning's equation says that the velocity is equal to hydraulic radius to the 2/3 times slope to the 1/2 over our roughness coefficient n. Velocity, as you know, velocity has units of length over time, dimensions of length over time. The hydraulic radius has dimensions of length because it's area over length, that's just length. So we get length to the power of 2/3. The slope is dimensionless because it's y over x, it has no dimensions. And then we have the dimensions of n, which at this point we don't really know yet, but we can find using this dimensional analysis. So by running this little dimensional analysis, we get that the dimensions of n have to be equal to length to the 2/3 divided by length and then multiplied by time. Length to the 2/3 over length, or divided by a length, would just give me 1 over length to the 1/3, right? So this is length over 3/3, my 2/3, there's length over 1/3. So we get that n has dimensions of time over length to the 1/3 in order for this equation to be dimensionally homogeneous. Now, because we're dealing with metric units, then the units of length will have to be time, which is seconds, over length to the 1/3, which would be meters to the 1/3. And this would give me values of velocity that are in meters per second. However, Robert Manning wanted to publish his results in Ireland, where he needed to use English units. In other words, if he needed the velocity to be in feet per second, so this is metric, and if he needed in English for the velocity to be in feet per second, then he needed to apply a conversion factor to these n values. Now, because these n values were already very popular in the day, people already recognize typical n values for typical materials. He thought it would be better, instead of having to convert the units, just apply a conversion factor to the equation as a whole. So he needed to find a conversion factor that would convert meters to the 1/3 over second to feet to the 1/3 over second. Seconds don't really matter, so really it's just meters to the 1/3 to feet to the 1/3. And that conversion factor is called K. So this conversion factor that Manning used was simply K. And what is K? K is my conversion factor from English to metric units, or from metric to English units. So what do we know about K? We know that there are 1.486 feet to the power of 1/3 in every meter to the power of 1/3. Which means that if K is 1.486 feet to the power of 1/3 in every meter to the power of 1/3, then K could also be simply 1 meter to the 1/3. And this is a K value that we'll typically see in Manning's equation. This conversion factor K then is applied to be 1.486 when we are dealing with English units. And it will be just 1 because there's no conversion necessary when we're dealing with metric units. And by applying this conversion factor, then Manning's equation becomes the equation that we already know, but with a K factor added. So we typically write it as K over N, the conversion factor over N, times hydraulic radius to the 2/3 times slope to the 1/2. Now, if we want to use Manning's equation to calculate flow rate, let's remember that flow rate is velocity times area. So all we have to do is multiply this expression times the area. And the typical way that we express Manning's equation for flow rate is K over N times area times hydraulic radius to the 2/3 times square root of the longitudinal slope. And this, or these, are what we collectively call Manning's equations. Again, it's the most common equation for this type of open channel flow. And we use it pretty much consistently in water resources engineering. Now, before I continue, before we start some examples, are there any questions? All right, if there are no questions, let's go ahead and work on some examples. On another note, I do have a lot of open channel flow videos linked to in the website. You can see where it says like mini lectures, because I did record these lectures last semester for my students that last semester. So if you do want more examples or something, and I also recorded some of my review sessions, you can always just click on them and see some of the other examples that we solved last semester. I think we're going to repeat some of the examples from last semester, but after we do the first couple of ones, I'm going to try to make new examples, okay? Anyway, let's start with 12.8. And this will be a simple example because it's a simple channel, and it'll allow us to just plug and play Manning's equation. I know I always mention that this course is not plug and chug, but Manning's equation pretty much is. As long as you know the channel geometry, you can find the flow rate pretty quickly. So in this example, we're actually given an orthogonal view of a rectangular concrete channel, right? Orthogonal view of a rectangular concrete channel. So if it's a rectangular concrete channel, then you can pretty much see it on your book. I'm gonna try my best to draw it, but essentially the rectangular channel looks something like this, where the water surface is here. Okay, and this is all the water surface. So what do we know from this rectangular channel? We are given a slope, and I mentioned that slopes are given in many different ways. We can be given slopes as percentages, slopes as simply ratios. So in this case, our slope is given as a ratio of 2 feet vertical for every 1,000 feet horizontal. So when you see this ratio, what this means is that for every 1,000 feet that you move horizontally, there is a 2-foot drop vertically. Okay, that's all it means. Okay. And we're also given some of the dimensions of the channel itself. We get that the base of the channel is 6 feet. So the base of this rectangle is 6 feet. And we get that the height of the channel, the depth, is 4 feet. Doesn't look like the depth is constant, but let's just keep in mind that this depth is uniform. Okay, I didn't draw it correctly, but let's keep in mind this depth is definitely uniform throughout the channel. All right. So given that information, I think we can try to use it to find the flow rate in this channel. And in fact, we can even use it to find the velocity in this channel. Now, the book tells us that the channel is made of finished concrete. Okay, and we are told that for a reach of 1,000 feet, we have a 2-foot drop in elevation. We would like to know the flow rate. And on top of that, I would like for you to give me the velocity as well. Now, the book tells us to take Mannings N for concrete to be 0.012, and that's actually a very common value for new concrete structures. However, if you're working in the field, you're not going to be working with new concrete structures. You typically want to analyze a structure after it deteriorates or considering the deterioration after some use. So in the civil engineering industry, we actually use a Manning's value of, or Manning's roughness coefficient of 0.013 for concrete. 0.012, again, it's possible, it's allowed, it can be accepted by the county who's reviewing your work. However, it doesn't take into account the potential damage to the structure that occurs with time. So 0.013, I think, is a more conservative and definitely a better number to use. So if we want to find the flow rate of an open channel, the first thing you want to think about is Manning's equation. So if you think of Manning's equation, you know that Manning's equation says that the flow rate is equal to K over N times the area times the hydraulic radius to the power 2/3 times the square root of the longitudinal slope. So we want to make sure that we have everything we need for this equation. So I'm going to start from left to right and look at all these terms and figure out what we need and what we already have. So if we look at our K value, K is a unit conversion factor. And that unit conversion factor really depends on the type of units that we're using. We mentioned that if we're dealing with metric units, we don't really need any conversion. So K is just 1. But if we're dealing with English units, what would our K be?
So it should be 1.486.
That's correct, 1.486. Yep, that's correct, 1.486. And of course, that's a conversion factor, so it'll be feet to the 1/3 divided by meters to the 1/3. Good, that's correct. You'll see that in your engineering reports, typically we don't show units for K. It's just common not to show them, okay? We look at N, and N is the roughness coefficient, and that roughness coefficient depends on the material of this channel. Now, because it is concrete, we're gonna use N to be equal to 0.013. Now, you don't have to expect someone to give you these N values. They're actually very common. So if you're ever working with a material and you're not sure its roughness coefficient, I can almost guarantee you that you can just Google whatever the material roughness coefficient and you'll get an N value for that material. For concrete, it's 0.013. For corrugated metal, it's 0.024. Asphalt, 0.016. High streams and brush is 0.035. Maybe overbanks with thick brushes with 0.045. They're actually very common. And you use them so much, you're going to use them so much in water resources that you're going to end up memorizing them, okay? We now turn to the geometric properties of this channel. So let's start with the easy property, which is the area. Remember that these properties are geometric properties of a cross section of the channel. So if I were to take a cross section of this channel, what would the area of the channel be?
Should be 24 feet squared.
That's correct, right? The area will be base times the depth. So it will be 6 feet times 4 feet, which, as you said, is 24 feet squared. Good. But now we turn to the hydraulic radius. We know the hydraulic radius is a ratio of the area to the wetted perimeter. We already know that the area is 24 feet squared. And as a recap, the wetted perimeter represents the portion of the cross section that's in contact with the channel. So what would that wetted perimeter be?
14 feet.
All right, that's correct. We get 4 feet from the side plus 6 feet, that's 10, plus another 4 feet, which gives us 14 feet. All right, so I'm just going to write it down, 4 feet plus 6 feet plus 4 feet. So we get that the hydraulic radius is 24 over 14 feet squared over foot is just foot. And 24 divided by 14 should give us about 1.71 feet. So good, we found our hydraulic radius. And finally, we end up with our longitudinal slope. Remember, our longitudinal slope represents the ratio of our drop in elevation to our longitudinal or horizontal distance traveled. So do we have information here to find the longitudinal slope? The answer is yes. We're given this ratio of every 2 vertical feet in drop for every 1,000 horizontal feet traveled. So our slope is just 2 feet over 1,000 feet. And we get a slope of 0.002. And of course, no units. You'll see that these small slopes are very common for open channels and very common for pipes. Typically for pipes, we want our slope to be about 2%, which would be 0.02 as a minimum or as a standard value. But we can even see slopes of 1% or even 0.5%. And for open channels, we'll see slopes of up even like 0.1%, which is 0.001. So our slope is already done. And look at that. We have everything we need to calculate the flow rate for this problem. We now see that applying Manning's equation, the flow rate will be equal to the conversion factor K, which is 1.486, over the roughness coefficient N, which is 0.013, times the area of flow, which is 24 feet squared, times the hydraulic radius to the power 2/3, which is 1.71 to the power 2/3. If you have a calculator, don't round until the very end. I'm rounding now because I wanted to look clean on the video. Times the square root of the slope, which would be the square root of 0.002. We plug those numbers into our calculator. What is our flow rate end up being?
Something I did. Oh, I got 7.32.
I would say, are you sure about that? Let's double check our units.
Is the velocity, I think.
But we're calculating flow rate.
I got 175.7.
175.7. Okay, so we get about 176 cubic feet per second. Yep, that's absolutely right. And of course, like you said, the velocity would be just the flow rate divided over the area. So my velocity would be 176 divided by the area. Again, don't round until the end. I'm rounding now because it looks better. Over my area, which is 24 square feet. And then we get a velocity of how much?
7.32.
7.32, thank you. Feet per second. And that's pretty much it. It doesn't seem very complicated because it isn't, right? Open channel flow is a very empirical method. It's actually very easy to follow, very, very easy to apply. And I think you're gonna have you're gonna have an easy time using Manning's equation, right? As long as you can calculate the area and the hydraulic radius, these geometric properties, you should be fine. Now, in order to understand how Manning's equation kind of works, let's look at a different scenario. Let's look at the case of a composite cross-section. In other words, a cross-section where the n value is actually not constant throughout the entire cross-section. Now, when we're looking at composite cross-sections, there's actually very different methods to use Manning's equation, and those methods will give us very different results. So we're going to go with an easier method, which is the one that the book uses, which is the weighted averages method, where we're going to look at our roughness coefficient as the weighted average of all the roughness coefficients. So let's go ahead and start with example 12.9. If you are interested, I do have, like I said, a video where I solved this example during a review session for last semester. So you can also check it out to see what questions the students had. And because the students typically come up with very good questions when we're trying to solve these types of problems. So for this problem, we are dealing with a composite channel. What we have is essentially something that looks like this. It's not going to be drawn to scale. So what we have is a concrete channel surrounded by a grass or natural overbank. I'm going to draw this representing grass. And this is going to be a very, very common type of channel that you'll see in your work as a water resources engineer. We'll see that flow typically for large storms does not remain contained within our channel and therefore must flow into the overbanks. So just to talk a little bit about some definitions, some terms, the concrete part is called the channel, which is where the flow is intended to travel. And then the outside part is called the overbank. Normally, when we design channels, we need to consider not just capacity, but we also need to consider an economic factor, right? If you know that a channel such as this will flood once every couple of years, you're not going to create a huge channel. Instead, you create a channel to contain most of the rainfall that falls in this area. And then you prepare or design your overbanks to contain that one or two special events where flow actually overflows into the overbank, right? So when we design our channels, especially roadway ditches, right, we want most of the flow to be conveyed within the ditch, and then some extra or additional flow from an unusual storm can be contained within the overbanks. And that's exactly what we're going to look at here. We're going to look at flow that is not just in the channel, but also in the overbank. And we would like to know the flow rate of this section. We could also calculate the velocity as well if we want to, okay? So what do we have here? We're given that we have an unfinished concrete section. Because the concrete is unfinished, we're actually going to use a higher n value because it hasn't been finished, right? So we have an n value of 0.014. And then we have overflow regions with light brush. And for light brush, we're going to have a Manning's roughness coefficient value of 0.050. Now, personally, I actually think this value is too high. For natural overbanks on rivers, we typically use 0.045 for heavy brush. And this seems, according to the figure in the book, this seems to be a pretty light overbank. So personally, I think this roughness coefficient is actually too high, but that is what the book gives us. So just for this problem, let's just use what the book is giving us. We're given some dimensions, right? We're told that the channel has dimensions of 2 meters by 1.5 meters. And we're told that flow is actually 2.5 meters deep. In other words, the depth above the channel will be 1 meter. The overbanks themselves are about 5 meters long each. And that's our channel. And now we want to find the flow rate. And because we want to find the flow rate, we're going to use Manning's equation. Here's the problem. We have multiple roughness coefficients, so we can't just plug in a value there. So just to get some ideas from you, how do you think we may be able to use Manning's equation? I'll write down the equation here so that we have it. If we want to apply Manning's equation, do you have any ideas on how we can reconcile the fact that there are different roughness coefficients?
Is it possible to segment into two different flow channels?
Yeah, that's a good option. In fact, that's the option that we're going to follow. Oh, I forgot to mention that the longitudinal slope is 0.0015. So longitudinal slope for the entire thing is 0.0015. And you're absolutely right. I think the best thing to do here would be to divide our channel. We look at the portion of the channel that's the portion of the flow that's pretty much in concrete, and we look at the portion of the flow that is on the light brush. If we divide it, you'll see that we end up with 2 or 3 sections, depending on how you want to look at them, right? We have the channel section, I'll just call this number 1. Then we have my overbank section, which I can call 2 and 3. Now we can treat them as one, or we can treat them separately. It doesn't matter because their n coefficient is actually the same. So we divided our channel into different sections. Now what?
We would just calculate our Q for each one and then add them together.
Okay, so when Nash says, let's just calculate flow rate individually. That's a good idea. We can calculate flow rate individually. All right, so we can do that. If we do that, then we get, right, that for our first term, which is the channel, our flow rate, Q1, will be equal to K over N, AR to 2/3 slope to the 1/2. So K over N1, the area of that channel, the hydraulic radius of that channel to the 2/3, and then the slope to the 1/2. The slope remains the same, so we don't have to segment it. We're dealing with metric units, so what is our K equal to?
1.
Okay, and we know that the roughness coefficient is 0.014 for this channel. What is the area of this channel? And remember, it's a flow area.
5 meters cubed.
5 meters cubed, okay. So where are we getting that number from, right? We get that the area should be equal to, we know that this is 2 meters, right?
Excuse me, squared.
Squared, right. We know this is 2 meters. And then for the area, you can see that our section actually includes the portion of the channel that's above the concrete channel, right? So that means that our other dimension should be 2.5, which, as you already said, equals 5 square meters. Now, this is something that where I want you to be careful. Several situations allow us to do this. Other times, this may not be appropriate. It really depends on the type of channel. It depends on the difference between the n coefficients, and it really depends on even the depth of the overbank flow. Now, there isn't a textbook solution for choosing the method you want to use. You can use this, and you'll find that for some channels, splitting your channel into these vertical segments doesn't give you realistic answers. So I do want you to be aware of that, especially for the take-home exam. Be aware that this methodology won't always work. And if that doesn't work, you're going to have to find different ways of reconciling these different roughness coefficients. But we're going to talk a little bit more about that later. What's the wetted perimeter for this channel? So we can calculate the hydraulic radius.
5.
5, that's correct. So we have 1.5 plus 2 plus 1.5. Remember, this section isn't included there because there is no friction from the channel on this section, right? So our perimeter, as we know, is simply 5 meters. Okay. So what does this give us? This gives us a hydraulic radius of 5 meters squared over 5 meters, which is just 1 meter. And we already know that our longitudinal slope was 0.0015. We can plug all these values into our Mannings equation and get a flow rate of how much? And while you're doing that, I'm just going to write the Mannings equation for the other section. So what is this flow rate equal to?
I got 13.83.
13.83, okay. So we get 13.83 cubic meters per second. Somebody has a different value, let me know. But for now, we look at 13.83 cubic meters per second. Good. My second and my third sections, based on the fact that they have the same roughness coefficient, we can actually treat them as one, or we can treat them separately. Because it's an example and we want to make sure we go over all the steps here for the purposes of this class, let's just treat them separately. We know that K was still 1, N will be 0.050 for both, and slope will be 0.0015. So we really need to focus on the area, the wetted perimeter, as well as the hydraulic radius. So what do you think is the area, the wetted perimeter, and the hydraulic radius? And let's suppose that we're only looking at section number 2. So section number 2, what's the area of flow?
Would it be 5?
That's correct. We have 5 meters times 1 meter. So that gives us an area of 5 meters squared. What about the wetted perimeter?
It should be,
Sorry?
I got 12 meters.
That's for the whole thing, right?
Yeah, yes.
If we're looking at only
I
one section, right, it would be 6, right?
Yeah, it'd be 6.
5 meters plus 1 meter is 6 meters. And then the hydraulic radius is 5 over 6 meters. What does 5 over 6 give us, just so that we can have a number here?
0.833.
Okay, 0.833. Good. We plug these numbers into Manning's equation and we get a flow rate for the second section of how much?
I got 3.43.
3.43, okay. And of course, we know that for my third section, the properties are actually all going to be equal to my second section. So how do we calculate the total flow rate here? Well, we just have to add up our individual flow rates. So we get the flow rate from section number 1 plus the flow rate from section number 2 plus the flow rate from section number 3. From section number 1, we have 13.8 meters cubed per second. And then from sections 2 and 3, we have 3.43 meters cubed per second each. So if we take all these terms, all these individual flow rates and add them up, what is the flow rate of this section?
22.66.
20 point what?
66.
66? I'll just round that up to 7. So 20.7 cubic meters per second. That is correct. Now, just a bit of an analysis question. If I ask you to calculate the velocity, would you calculate the individual velocities and also add them up to get the velocity?
I would just take the total area and divide the total Q.
That's correct. And if we do this, we can actually see, velocity is just Q over. If we do this, we'll see that velocity really ends up being nothing more than a weighted sum of the individual velocities in the section. So if we do Q over A, we just get 20.7 cubic meters per second divided by all of the areas, right? And the sum of all three areas would be 5 meters squared plus 5 meters squared plus 5 meters squared, so just 15 meters squared. So how much does that give me in velocity?
Mm, 1.38.
Good. And this is typically known as the average velocity in the channel. Now, you should know, right? And if you don't, then you'll know now. You should know that the velocity in the concrete channel is probably going to have to be a lot greater than the velocity in the overbank, right? So this 1.38 is actually the average velocity throughout our entire channel. It cannot be the velocity everywhere, right? It's actually the average velocity. So realistically, right, the velocity in the channel will be greater than 1.38. The velocity in the overbanks should be smaller, right, than 1.38. Now, another thing you can do if you want to calculate individual velocities, and if you want to calculate individual velocities, you can just use Manning's equation for each section individually. And if you want to then get the average velocity, just do a weighted sum, right? You have individual velocities, multiply each of them by their areas, which gives you the flow rate, add them up, and then divide by the sum of the areas, which is exactly what we're doing here, right? This is the individual velocities multiplied by their areas and then add it up. And this is the sum of their areas. Now, why do you think it's important, or it would be important to calculate individual velocities? Why can't I just say that I have an average velocity for the whole thing? Why would I need individual ones?
Because your velocity of fluid over a certain surface will affect the performance of the fluid over that surface.
Exactly, right? And then from a more engineering standpoint, we can also think of shear stresses and erosion, right? Erosion is directly related to the velocity. You want to look at erosion in a channel, you need to know the velocity at that part of the channel. So these are all, I'm glad that you're all understanding this, because this is what you're going to do in the take-home exam. But this is essentially Manning's equation, right? This is essentially open channel flow. And you'll see that the problems that you have in the book for open channel flow are pretty much the same, in that all you have to do is apply Manning's equation. You can apply it to individual channels. You can apply it to different sections. But because these are still empirical equations, sometimes we may need to turn to other resources in order to learn how to use Manning's equation. So one helpful tool, I would say, that I would recommend that everybody that's dealing with open channels look at is the Heckgrass Hydraulic Reference Manual. Now, I want to give you a little bit of an introduction to what Heckgrass is, because I think it'll be very helpful for your careers if you ever end up working in the civil engineering field, but also for your academic stuff if you ever end up taking, let's say, a take-home exam in the topic of open channel flow. So Heckgrass is a hydraulic model. It's a computer program that allows us to model these sections. So you model these sections using station and elevation points, so given coordinates to each point, and then you assign different roughness values to the section, and it'll calculate the flow rate. Now, the hydraulic reference manual is it's not really a user manual because it doesn't teach you how to use the program. HECRAS has its own user manual, but the hydraulic reference manual tells you how the program calculates its values. And I think it's a very, very good resource. In fact, you'll see that most water resource engineers, we will cite the hydraulic reference manual or reference it because they did the job of compiling together all these different methods for calculating flow rates in open channel flow. And you'll see that sometimes if this methodology of splitting up your section doesn't give you realistic results, you're going to have to look at other types of methods. Things like taking weighted averages of your roughness coefficient or things like that. And you can find all these different methods compiled in the hydraulic reference manual. Now, the good thing from a career perspective is that as long as you understand the methodology, you don't really have to calculate yourself because the program does it for you. But it is still your responsibility to understand the methodology, right? You should still know which method you want to use and why you want to use it. So hopefully this brief introduction to open channel flows has been helpful for you. And I'm gonna recommend that you just work on your homework problems for this week. And like I said, you'll see that they're pretty much all the same using Mannings equation. Try to solve them anyway, even though you're just repeating the same equation over and over again, because the more you solve problems like this, the more you're gonna get used to Mannings equation.